Hello everyone. My name is Edward Ma. I'm an engineer with Hewlett Packard Enterprise, and today I'm going to be talking about a data connector that we've got that efficiently moves data from Vertica to Spark. Now, Apache Spark, I'm sure, needs no introduction. It's a very popular data computation engine because it has excellent integration with the Hadoop ecosystem, and it's been shown to have good performance in some cases. It's very popular. But for all of its merits, it does have some limitations, one of which is that it is not a database. So it does have some limitations when it comes to persistent data storage. But luckily, the makers of Spark know this, and so they have provided many APIs that allow you to integrate with external data. And one such external data source that's possible is our Vertica database. It's our bread and butter database. It's very fast, supports analytics at scale, and we like to think that it's an ideal data source for Spark. So the particular API that we avail ourselves of is the external data source API, which is part of Spark SQL. Now, if you're not familiar with Spark SQL is a part of Spark that allows you to look at data either in Spark or outside of Spark from a database-like relational sort of way. You can do projection and filters on your data. For example, if I've got a data frame and I have two columns that I want, I can get those two columns using a .select. And if I wanted to push a filter predicate where getting all the rows where age is less than 50, I can also do that. Now, the cool thing is that you can give it a custom Scala library, which is what we've done, which tells Spark that this data is going to come from there, and to let that code handle creating the Spark's job for moving the data. And the other cool thing is that these filter and projection operations can be pushed down directly to the source, improving efficiency. Now our approach addresses a key property of Spark, which is that it doesn't have a simple batch scheduler. It can get clever, so it can schedule one or a subset of the many tasks that make up a Spark job independently, one at a time or some at a time, depending on system resources. And as such, the tasks that make up a job, when you write a job, have to be able to function independently, and you have to write your job such that you don't coordinate them together. And our solution is simply to have these tasks each issue a direct query to Vertica. Now, the advantage of having this parallel query approach is that the filter and projection pushdowns are trivial. Each query can have the same predicates, and they can be safely and independently executed, independently of one another. Now, the key innovation that is interesting about this work is how we leverage data locality. Imagine that you have a 4-node Vertica cluster. The table data is going to be segmented based on a hash function. Now imagine that this ring represents the range of values that you might get after running a tuple through the hash function. There are 4 quadrants to this circle, each quadrant representing a node. So if the tuple hashes to that quadrant, then it goes to that node. So the particular approach that we have maps every Spark partition or Spark task to some range on this hash ring. Let's say 0 to x and x to y. And notice that these ranges are perfectly contained within one segment. There are no overlaps, and they don't bleed over the boundaries. That is the key to our approach. That means that when I issue a query to Vertica, that task can be served only by that particular node, and I don't have to get data from the other nodes of Vertica. And so basically, we do that by issuing queries that look like this. So the one at the top might look like that, where we have a predicate where hash is greater than 0 and less than x. The other one greater than x and less than y. This gives us the nice data locality property that we want. Now, Vertica is a distributed database, and as such, usually when you query it, it expects that you might have data from all of the nodes. So the query processor and the query optimizer has to be told, in this particular case, even though we know each query can be served by one node, the processor doesn't know that, the optimizer doesn't know that. And so it will generate a multi-node plan and tell everybody to run the query, which is not necessary. And so one optimization that we give it is giving what is called a query hint, an optimizer hint, whereby we just tell it this query can be run locally on the initiator. And those two things basically form our design, and basically with these two things in place, we have both the benefit of there being no traffic between Vertica nodes, and all the other executor nodes don't have to waste CPU resources running the queries. I'm out of time, but I had some performance figures here that shows that the approach scales linearly, and the push-down approach works well as well. Thanks.